Oh, there we go. So yeah, thank you to the organizers, and thank you for everyone for coming. Yeah, I'm going to talk about a fluids problem in sort of an amplitudes method, and it's with Cliff. And I should, oh yeah, here's the reference. And I should point out, I think Zoom has my names, my old name, but Slack has, I took my wife's name, so it's a lot simpler. So anyway, yeah, there might be some name confusion for a while. Okay, so before going to fluids, I just want to take a step back and think about why Yang-Mills play so nicely with amplitudes. And I think it's more or less because Yang-Mills has four really excellent properties for amplitudes. You could name more, but certainly these four are super important. So the first is that Yang-Mills is fundamentally trivalent. All the basic interactions are 3-point. Yang-Mills is colored. It's the waves are transverse or massless or gauge invariant, however you want to think about it. Turns out transverse will be the idea that generalizes best. And of course, Yang-Mills is Lorentz invariant. And combinations of these properties give rise to just a tremendous amount of rich structure. So for example, BCJ is sort of a combination of trivalent and color, and think of Weinberg-Soft theorem as sort of a combination of trivalent and gauge, and so on and so forth. So if you want to look for a new theory or some theory that plays nice with amplitudes, it'd be nice to have some of these properties. And Navier-Stokes has two of them, just to start with. So it's trivalent and transverse, or at least if you look at an incompressible fluid or solenoidal fluid, or however you want to say it. So just as a reminder, the Navier-Stokes equations, you can get them from the conservation of energy momentum for a perfect fluid in a non-relativistic limit, where the fluid has some velocity field u and some energy density rho and a pressure p, and the fluid is, there's some friction associated with the fluid, so there's some viscosity nu. And you get something that looks like this, but we can make it look a little bit nicer for amplitudes if you just slap a color on everything. So you're just trying to go from photons to gluons, essentially. And so you just put a color index everywhere. You have to put in a structure constant. And now you have three of the four properties, essentially, that Yang-Mills has. So now you have pretty good chance of finding something nice in amplitudes. Now, the first step is sort of a technical one. You just want to integrate out the pressure. And you just solve for the pressure and plug it back in. And now I have an equation purely in terms of the field u, the velocity field, and some sources. And so this is mostly what I'm going to focus on. This sort of non-abelian fluid is mostly what I'm going to focus on. But there are a few things that I'll talk about that will actually work for the abelian, for normal Navier-Stokes. Sort of part of the motivation for this is that Navier-Stokes doesn't come from an action containing only the fluid degrees of freedom. There are ways of extending it and doubling degrees of freedom, and so on and so forth. But when you don't have, or when there isn't a clear Lagrangian, it's sort of tempting to try on-shell methods, to try amplitudes. Okay, so the goal will be to study the amplitudes of this non-abelian fluid. And basically, you can go through any review article or any textbook and see if it worked for Yang-Mills. Let's try it for fluids and see if it works for this non-abelian fluid. Okay, the first step towards getting amplitudes will, of course, be to go to Fourier space. And the transverse condition, as I keep emphasizing, pops up as an on-shell condition. And your dispersion relation is a non-relativistic one. And this factor of I is just signifying that the waves disperse, that there's some friction. Okay, so when someone, is it getting cut off in the bottom? That's unfortunate. Oh, there we go. Maybe that's a little better. Yay. Oh, well, okay. So when someone hands you a PDE, you're essentially looking for, or Navier-Stokes, you're essentially looking for a classical solution or a tree solution. And the method I'm going to use is essentially Brenzgela recursion, or it's essentially a Born series. So the idea will be to formally solve for the fluid velocity u in terms of a bunch of on-shell sources. So you're essentially constructing a one-point function for u. So solve formally the equations of motion. I've done it just schematically. for u, and now I iteratively plug back in till I obtain u as however, to whatever order I want as a function of a bunch of on-shell sources. Now this was done by Wild in the 60s for the abelian case, but of course we're going to focus on the non-abelian one. Okay, so just to make this super clear, this sort of tree picture, I really can't associate something that looks like a tree amplitude to it. And in fact, it looks even, well, I'll get to it, but I've drawn a tree here because it really does look like a tree. But essentially what you're doing is calculating a semi-on-shell tree amplitude. I'm going to put all the sources on shell, amputate their propagators, normal kind of stuff. I'm always going to keep this, so I have a bunch of on-shell sources up here. I have the special leg, the U down here, which I'll always take to be the nth leg, and it will be off-shell. And just the naming convention is kind of cute, that I will call the U to be the root leg, since it sort of looks like the trunk or root of the tree. And all these sources I'll call leaf legs, because they sort of look like the leaves of a tree. Yeah, I think that's all I had to say for that. So next I should write down the Feynman rules. And it just looks, the propagator just looks like 1 over the dispersion relation. I'm drawing straight lines with arrows because you have to keep track of the direction of energy flow. Even though I'm sort of thinking of these things as gluons, I haven't drawn googly lines. I want to keep track of that direction, so I've drawn straight lines with arrows. The interaction looks sort of similar from Yang-Mills. There's a structure constant, a bunch of momenta. The point here is that you do have to keep your track of the direction of things, of energy flow. And it's quite easy to, using the solenoidal or transverse condition, to rewrite this interaction so it's proportional to the momentum of the incoming leg. So that's quite handy. And so just to keep everything, just for notation, capital A, B, and C will be particle labels for the rest of the talk. Lowercase a, b, and c will be color indices, and spatial indices will be I, J, and K. Okay, so we will get a lot of mileage out of just rewriting the propagator and the vertex. So let's start with the propagator. If I look at the propagator deep in some tree amplitude, and I use the on-shell conditions, I can actually eliminate all the energies. And the propagator is naturally expressed nicely as just a function of a product of a dot product of 3 momenta. And so this looks really reminiscent of a relativistic system where it's described entirely in terms of manosyms. That is, the energies don't appear anywhere. It's all going to be a function of P dot P, P dot E, stuff like this. So the other thing I learned is the effective coupling constant for the theory is 1 over nu. That is, the vertices are independent of a coupling constant. The only place the coupling constant shows up is in the propagator. So this series solution we're constructing is going to be a good approximation when nu is large. That is, when you have laminar flow, or in other words, when the fluid is highly dissipative. So you sort of hit it and the waves quickly dissipate. Okay, so just to quickly flash the 3 and 4 point amplitudes, they look quite reasonable. They're functions of manostams. They are in fact energy independent as advertised. And something that you can show from the Feynman rules, which will be useful later, but you can see in the examples here, is that the amplitudes, there are no P dot P terms in the numerators of the diagrams, and that will be quite helpful. In fact, the only manostams that show up in the numerator of the amplitudes will be E dot E, where one of the polarizations is the root leg, and P dot E terms. Okay, so you can also come up with a you can use the spinor helicity formalism. It was originally developed for cosmological spacetimes, and the idea is basically you just define P0 so that P squared with a Lorentz metric is 0. So for us, this is just going to be P0 is the square root of energy. And now you can do some slightly funny things. I mean, of course, in 4D spinor helicity, you have 2 invariant tensors. You have epsilon AB, epsilon A dot B dot. But now you have another one associated with rotations, non-relativistic rotations, which is epsilon A B dot. So you can do funny things like construct or contract angle and square spinners, which will essentially just be energies. That is, the things preserved by rotations. So the 3 point amplitudes look very nice. The numerator just looks like whatever you need in order to get the right helicity weights for the spin of the particles. And the numerators are just the energies of particles 1 and 2. That is the non-Brief legs. And you can write the MHV amplitude for the fluid, and it looks exactly like the MHV amplitude for Yang-Mills with the function of the particle energies tacked on. Now, it'd be nice if this extended, if you could get an MHV decomposition, if this went beyond 3-point to 4-point. It may, but it's a little, it's not quite as clear how to do that because the propagators don't factorize quite so nicely into holomorphic and anti-holomorphic pieces like they do in Lorentz theories. Okay, so I said it would be useful to rewrite the propagator and the vertex. For the propagator, we learned a lot of nice things like the coupling constant and everything will be a function of Mandelstams. If you do it for the vertex now, you immediately get a soft theorem for the root leg. That is, you can rewrite, like I said before, you can rewrite the vertex so it's proportional to the incoming momentum. In this case, the root leg. So you just trivially get an Adler zero for the root leg, just be rewriting the Feynman diagrams just a little. And you get soft theorems for all the other legs too. So you go essentially, you get a Weinberg soft theorem for all of the leaf legs. And here I've written it, I mean, you get exactly Weinberg soft factor. Everything is normal. I've color ordered everything to make it look a bit nicer. The one tiny caveat is that if your soft leg PI is adjacent to your to the root leg, then you have to drop one of these factors. But essentially, everyone has a soft factor or soft theorem. Okay, since there isn't really an action containing only the fluid degrees of freedom, you might look for some on-shell construction of the theory. So, given some small amount of seed data, like 3 and 4-point, can you construct the entire theory? And of course, the way to automate this is with recursion. So I'm gonna show 2 recursion relations. The first one, you shift all of the leaf leg momenta by their polarization vectors. And so long as you work with circularly polarized, not gluons, but fluid particles, this will maintain the on-shell conditions. And since you're just shifting the momenta, this essentially just counts the mass dimension of the theory, which is exactly the same as that of Yang-Mills. So this should be able to construct 5-point and higher. I was completely agnostic about these parameters, these taus. So if you choose them carefully, in other words, you choose them so that you probe an Adler zero, you can in fact construct 4-point. The other thing to notice is that the poles are quadratic here, similar to a soft shift. There are going to be z-squared terms in the denominators. Okay, there's also a Resog type deformation you can do, where you shift the polarization vectors and the momentum vectors in opposite directions using some nilpotent reference vector that I'm going to assume is orthogonal to the root polarization vector. Now, this is quite fun because if you go back to the fact that I said there are no p dot p terms in the numerators, you realize that this shift doesn't affect the numerators of any of the diagrams. That is e dot e, that's z independent. P dot e, that's z independent because there's this sign difference. So this only picks up poles when you have poles from Feynman diagrams. So this is just going to reconstruct Feynman diagrams for you. And it's sort of cute that a Resog shift for this non-abelian fluid will essentially give you Feynman diagrams, where for Yang-Mills, the Resog shift gives you the MHV decomposition. Okay, sort of the crowning jewel of this picture is that you will get off-shell kinematics, color kinematics duality for free. So if I look at some ST and U diagrams embedded in some larger process, if I just use the transversality condition to rewrite the numerators a little, I immediately find that the numerators off-shell all sum to 0. And the reason that you get this sort of magic for free is, I think, secretly because, again, you don't have these p dot p terms that you can shuffle between the ST and U channels. Okay, now that we have color kinematics duality, we should try to double copy. And you can do it directly at the equations of motion level. So before I go and do that, let me just rewrite this fluid equation a little bit by introducing the kinematic analog of the structure constant. which I call FIJK, and it's familiar from self-Dewey Yang-Mills and from pions for constructing the double copy off shell for pions, and it just looks like a commutator with a derivative. And funnily enough, this thing is, if you think about vectors in sort of a GR way, it's just a generator of translations. It generates the Diffio algebra. Anyway, so now that I have color kinematics off shell, to get the double copy at the EOM level, all you do is replace all the, you take every color index and make it a spatial index, and replace all the appropriate structure constants. And when you do, you get something that looks like some tensor fluid. And if any of you have seen this PDE before, I'd love to know. But it looks like some kind of tensor fluid. Okay, so now that you have double copy, color kinematics duality, let's try it for some extended solution. Let's try it at the classical level. So I will look for a Toth polycop type monopole. I'm going to assume the monopole is spherically symmetric, static, and I'm going to work with SU2 just because this means I can put spatial and color indices on the same structure constant. And then you can just plug into the equation of motion to look for some, and you get some nonlinear but ordinary differential equation for this structure or shape function for the monopole. And you can do the same thing for the tensor fluid. Of course, it has to be symmetric in its two indices. So there are really two things you can write down: some function that's proportional to the metric, and some function that's proportional to the positions. And when you solve this, you get something that's extraordinarily reminiscent of Kirchhoff. That is the fluid monopole. Looks somewhat like a point charge, and the sort of gravity solution, or the tensor fluid solution, looks like a flat piece plus the gauge piece squared. Okay, the last thing I want to talk about is how do you get currents and symmetries? How do you deal with them without a Lagrangian, or how would you approach them? And there are two symmetries, two global symmetries. There's a color symmetry associated with the structure constants, where you're essentially just doing a global color rotation. And the kinematic symmetry associated with those structure constants is just going to be a translation. The best way to get the current is just guess. It's a very amplitudesy kind of thing. Just guess and make sure it has basic right properties. And so for the kinematic current, you guess something that looks like this, and you find that it's conserved, or it's divergenceless up to time derivative pieces. And this allows you to find essentially the dissipation rate of total kinematic charge. And this total kinematic charge should be conserved just by Stokes' theorem. So you can make some progress with current symmetries and currents, even though you don't necessarily have a Lagrangian. Okay, so just to summarize, I think there are two main takeaways, at least for me. The first is that Yang-Mills and fluids share a lot in common. And the other is that we can apply some of our amplitudes techniques directly at the equation of the motion level without necessarily having a Lagrangian. And there are lots of topics that I mean, that's a lot of green check marks, but there are lots of things that would be interesting to try. There are lots of, can you try, is there a KLT kernel, so on and so forth. So there are lots of interesting things left to check on. So I think I'll end there. Ooh, a minute early. Woo. So yeah, does anyone have any questions?
Yes, thanks, James. And now, if anyone has questions, please try to raise the hand. And yes, Lance.
Hi, James. Thanks for that nice talk.
Thanks.
So I can think of this as a multi-component classical fluid then? And if so, I mean, is there a sort of a picture you have of what this non-abelian interaction does? It's exchanging velocity, it's altering velocities of the different components while preserving various things? And is it easy to see there's only one of those such interactions?
I mean, is the theory sort of unique in some way?
Yeah. Or also just, what do you picture when you picture these fluids, a multi-component fluid moving around, which is, I guess, what you picture, huh?
Yeah, I don't necessarily have the best intuition for what the fluid really looks like. You know, I mean, it's obviously not water, you know, some obvious fluid that you're used to. So yeah, having the best intuition for exactly what it looks like in a real world sense, I don't have that, unfortunately. But it is, you can show it's essentially, there aren't a lot of interactions you can write down. So I think you were sort of asking also about a uniqueness question, and it is basically unique if you assume power counting and you assume it's incompressible, like Yang-Mills, that's pretty much all you're left with. So it's pretty much unique in that sense. You could try adding higher derivative operators, which is also an interesting, you know, can you get some f squared, f cubed kind of ideas going on? But at this level, it's more or less fixed.
Yeah, I was also wondering if there was any way you could derive it from a relativistic setting by making the vectors massive by Higgsing and going to threshold, but I can't see how to do that because the 1 goes to 2 splitting. If the thing, you would have to have the mass of the things they're splitting into be m/2 or something in order to make it a threshold, a low momentum process. So it doesn't look like it comes out of a relativistic theory directly. Am I wrong about that, or?
I might have to rely on my lawyer here, because I know things, but I'm not supposed to share certain things.
Okay.
But let me say, I mean,
so it's not impossible.
let me say, I mean, of course you can obtain Navier-Stokes from a relativistic fluid by taking a non-relativistic limit.
That's different from obtaining it, you know, from relativistic Barron's-Gila or something like that, probably.
Right, yeah. That's true.